Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through angles and constraints in trigonometry. So this is actually the third lesson that I teach in my trigonometry unit. So I'm going to go ahead and work through my notes, so therefore you can see me working through multiple problems and get the solutions that I covered in my class. So what we're going to talk about in this lesson is basically just how to identify the quadrants that an angle lies in, how to evaluate the 6 trigonometric functions given a triangle and constraint, as well as to evaluate the 6 trigonometric functions when given a point. And you might notice this is very similar to kind of what we've already covered in day 1 of our first lesson. And that is true because actually this is like a little overflow of problems that I decided I wanted to separate from the first 2 lessons to kind of create it as its own lesson. However, in a typical textbook, you would see these combined with either in day 1 or in day 2's lesson, either in right triangles or in the angles in trigonometry unit. But I wanted to give them a little of their due because students have trouble with identifying the quadrants. It's not so much labeling the quadrants, but it's just understanding that process of the constraints for the functions. So either way, let's go ahead and get started on how I started this lesson, which is basically just asking students to plot a point. Now, I know it kind of sounds like a little elementary task to give some students, but there's a couple of key points that I wanted to make sure students understood. The first thing is that, again, these are coordinate points. These are x and y, right? So x from the origin, x tells us the horizontal distance away from the origin, and y is going to give us this vertical distance away from the origin. So you can go over 1, up 2, right? You're not doing, I remember when I taught Algebra 1, sometimes we'd have students do this. Well, that's like 2 points, right? So you're not plotting 2 points, you're just plotting 1 point. So it has a x and a y coordinate, right? So that was kind of like that important idea here. It's just understanding those distances because that's going to come up in this lesson. The other thing was like estimating. I'm not big on students being able to, how correct they are on their graphing, but I wanted them to understand, 2/3, that's larger than 1/2. Forget about the negative. It's larger than 1/2, but less than 1. It's actually 0.666 repeating, right? But so just as long as you can estimate, and like you can even see my graph is not that great, but at least just understanding where that should lie if I was going to graph it. And then also the square root gets a lot of students as well because they're like, I don't know the square root of 2. You're right. Probably most of you do not know the square root of 2. And if you don't have a calculator, what do you do? Well, in my case, I just like for them to understand, the square root of 1 and the square root of 4. So, the square root of 2 is going to be somewhere in between 1 and 2, right? And it's going to be closer to 1 than it is to 2 because we have the square root of 3 in there as well. And then the last thing I just wanted students to recognize when they're plotting these points is notice that each point is in a different quadrant. And the reason why they're in a different quadrant is either the x or the y or both are going to be negative, right? In the first quadrant, my point is positive. Whereas this second quadrant, my x coordinate is negative. Third quadrant, they're both negative. And in this fourth quadrant, the y coordinate is negative. And I kind of gave away my quadrants, but that was something I wanted students to, I tried to remind them of, which was that the coordinate points, or the quadrants that we have previously studied, quadrant 1, quadrant 2, quadrant 3, quadrant 4. And this is something that we do refer to throughout this lesson and in later lessons. So it's just important for students to remember those quadrants. Now I already kind of talked about this, but as in that warm-up, but this is what one thing I wanted students to basically go ahead and see is, this little summary here. So in quadrant 1, the coordinate point xy is always positive. And that's what's awesome about quadrant 1. X and y are positive. Like when I know something is in the first quadrant, this is going to be really helpful. We know that x and y are going to be positive. In the second quadrant, you can see that the x is negative. The y is positive. And you can just kind of see this little summary of information. So again, I kind of like wrote them out here, but I think just understanding this figure here is going to be really just kind of helpful to remember. So now is where we start to make this kind of jump now into a triangle in the quadrants. Because previously, when we were doing triangles, like in day 1, we just had a triangle in space, right? It was just some random right triangle in space. There was no up, there was no down, there was no left, there was no right. It was just a triangle in space. So the point was, even though we always just did positive numbers, but negative numbers really made no sense. Well, now we're putting triangles in a xy axis in the in the quadrant system here, or in this coordinate grid. So therefore, now we need to take into consideration the directions that we need to take into consideration the orientation of the triangle. So I kind of worked through this, but I just want to kind of step my way back and kind of do how I started this. So I first started this with the xy. We knew that x represented the, here's the point. X represents this distance over, and y represents the distance up. Now, we can create a triangle by obviously drawing a direct angle towards the origin. And if you were to think about that, you could say, well, what should we call that? That's the hypotenuse. And some people like to call it C or H or, whatever case. We're going to go ahead and use R, and you'll see why. We'll call it R in a later lesson. But for my point is, let's just understand what is R representing in this case. R is representing the direct distance from the origin to the point, right? We have the horizontal distance, we have the vertical distance. R is like the direct distance, right? If you could instead of walking that street, if you could run directly to that point, that would represent R. Now, obviously in the triangle here, you can see that it is the hypotenuse. Now, there's also a couple of key points here. Notice how my right angle is going to be perpendicular with the x-axis, and that my angle here is at the origin, has a vertex at the origin, and it's also between the terminal side and the x-axis. So this is what we call our central angle. But this is really important to make sure you understand how this triangle is drawn, because sometimes students will draw the triangle like this, and sometimes students will draw the triangle like this. Now, obviously, this is going to be taken into consideration like x and y, which is not going to work, and this one is not going to work. And the reason why it's not going to work is because notice these angles that I have here, and this is really important to understand. When I reflect this, when I take this point and reflect it over here, you notice that the x just changed the same, right? The y coordinate remains the same, the r coordinate remains the same. The only thing that changes is the x. And then I say, look at the angle theta. The angle theta, again, if we're just reflecting this triangle, that is the same, right? So this angle is the same. Then I say, well, what does this angle really look like? How can we kind of maybe conceptualize, understand based on last chapter or last lesson what that angle is? And you can say that that is the reference angle, right? If blue represents my angle, this point here would represent the reference angle. And that is true for this angle, for that angle, and for that angle. They all represent the reference angle. And that is extremely important, because once we get into our next lesson, we are going to be talking more and more about the reference angle. So last class period, we just really introduced the reference angle and kind of showed students how to find it. Next lesson, we're going to actually be utilizing the reference angle to help us solve problems. So if you drew your triangle like this or this, you notice that these are not reference angles, right? The reference angle is between the terminal side and the x-axis. So basically, I kind of just ended up with my students. When you're drawing a triangle, because we are going to be drawing our own triangles in today's lesson, if it doesn't look like one of these triangles, then it's going to be wrong. So make sure you're drawing your triangle here. We're representing these as reference angles or as central angles, where basically the vertex is going to be at the origin, and your angle is going to be the terminal side between the side as well as the x-axis. So just make sure it's always with the x-axis. You can always make your triangle perpendicular to the x-axis, not the y-axis, all right? And then the only other thing that I also talked about is, the difference here with all these triangles is they're just reflections. This is reflected about the y-axis, then this is reflected about the x-axis, and then you reflect it over. So you can see how the side lengths now change based on which quadrant they're in, right? But the one thing that does not change is r. R remains the same. R is always positive. And again, if you just think about what R represents that direct distance from the origin to that coordinate point. So of course R is always going to be positive. It doesn't matter which quadrant it's in, the orientation, R is that direct distance, right? So it doesn't have any direction to it. And that's going to be very helpful for us in this lesson to understand that it's that direct distance. But last but not least is when we were looking at this, and we did spend a lot of time like I'm doing now. Since we have these new triangles with x and y's and r's, that means our previous trigonometric definitions, we can actually update those from day one. So let's go ahead and take a look at some new trigonometric functions. And they're not really new trigonometric functions. They're the same trigonometric functions. They're just a new way of basically describing them. So, here's the triangle in the first quadrant again. We can see if here's our angle theta, right? We remember sine, right? Sine of theta was opposite over hypotenuse. And that's still the case, opposite over hypotenuse. But now when we're talking about this in a chording grid and not some random triangle in space, we can use y over r, where again, r represents the hypotenuse, right? Or it's also that direct distance here from the origin to the point. So sine of theta is y over r, so therefore cosecant of theta you can see again is the reciprocal, it's just r over y. Cosine and secant, again, are reciprocals of each other, and tangent and cotangent are reciprocals of each other. Now, there's something else that really plays into this that's important to understand because, you know, positive and negatives, as I mentioned, like now make sense, right? They are important. So if sine is negative, right, r is always positive. So if sine is negative, that means y is negative. So if sine is negative, cosecant has to be negative, right? If y is negative, then y is going to be negative over there. If the cosine is negative, then the secant is going to be negative. The tangent is negative, the cotangent is going to be negative. So that's one thing I'm looking at when I'm grading. You know, if I know that we're in a certain quadrant, I know that both sine and cosecant are going to be negative, right? Because basically they're the same reciprocal, they're the same sides of the triangle, just, you know, different comparisons, either opposite or hypotenuse over opposite. So they're both definitely going to have the same sign, either as positive or negative. Now, it does get a little tricky here with tangent and cotangent, just in the fact of like, if I know it's negative, I don't know if it's the y or the x that's negative, right? Because typically we write that x in front or the negative in front, but it could be one or the other. So that's what we're going to be basically discussing today is how to determine which is going to be negative, because you could have a negative in the numerator, you could have a negative in the denominator, you just can't have it in both. The other thing is also if it's positive, that could be a positive y over a positive x, or it could be a negative y over a negative x. So dealing with tangent and cotangent sometimes can get a little tricky, and that's obviously what we're going to cover here in this lesson. So before we get started though, there's one last topic that we want to cover, which is basically just understanding the trig functions in the constraints. So if you remember, you know, here's just me redrawing all the triangles now in each quadrant. And if you remember the trigonometric functions, right? You know, sine is y over r, cosine is x over r, tangent is y over x. You can notice that in the first quadrant, since x and y are always positive, that the sine, cosine, and tangent are always going to be positive. In addition, if sine, cosine, and tangent are positive, therefore cosecant, secant, and cotangent are positive. So I didn't even write them in there because we now already know that the reciprocals are also going to be positive. And we're going to get faster at this, but, you know, I'll just kind of go through the first summary out here. If we're in the second quadrant, we know that the x is negative. So any trigonometric function which is when x is included, then is going to be negative. For instance, cosine and secant will be negative for any angle that's in the second quadrant, as well as tangent and cotangent, because those are, you know, tangents y over x, y over negative x, and cotangents negative x over positive y. So of course, those are going to be negative in the second quadrant. When we look at the third quadrant, you notice that a negative x and a negative y. So obviously, cosine's negative, secant's negative, sine's negative, cosecant's negative. However, the tangent, though, is going to be positive because negative y over negative x is positive, or cotangent, negative x over negative y is positive as well. So you can see here, you know, basically the x, both of them negative. And then last but not least, the fourth quadrant, the y-coordinate's negative. So now my sine and cosecant are negative, but also my tangent and my cotangent are going to be negative. So that is just kind of like this little summary of ideas. And again, you don't need to like memorize these or write these down. You know, I just told my students, but it is a good idea to just kind of see how we can identify without actually evaluating the trigonometric functions. We can just see if they're going to be positive or negative just based on knowing which quadrant they lie in. All right, so now let's go ahead and determine the quadrant. So fairly basic, right? We have our 4-quadrant system, and we're just going to practice drawing the triangle in the correct quadrant system. So there's a couple different ways that I'll present students with them. The best way is just tell them which quadrant the angle lies in. But a lot of times we're going to be given some trigonometric inequalities. So for instance, this one says cosecant of x, remember x in this case is the angle, cosecant of x is less than 0. Well, again, that's really just a fancy way of saying something is negative. So if cosecant is negative, what does that mean? So remember, cosecant of an angle is your hypotenuse r over y. Well, r is always positive. That means y is negative. So then which quadrant is y going to be negative? Well, y is going to be negative in the third and the fourth quadrant, right? Because if the y coordinate is negative, it's going to be down here. So it has to be in one of these two options. And then cotangent of x is greater than 0. Again, that's just a nice fancy way of saying something is positive. So cotangent, it represents the x over the y. Now again, as I mentioned, that is important because x over y could be positive x over positive y, or it could be negative x over negative y. Basically giving me the option for the first as well as the third quadrant. And therefore, what you can see is, I'm not really doing this plus or minus, but you can see that in the third quadrant, that is the only quadrant where both of these restrictions are true. So therefore, I can just draw my triangle. I'm going to use the same angle x, and again, I'll kind of further explain this later, but because even though it represents the reference angle here, but I'm go ahead and graph that same triangle in the third quadrant and just make sure I graph it the way that we kind of, discussed from the beginning. In the next example here, I have 270 degrees is less than some symbol that we have not discussed yet in my class is less than 360 degrees. And I joked to my students, I said, hey, you don't know what that symbol is, so, hey, we should just not do a problem, right? And they're like, yeah, sure, why not? What is that? But again, that is phi. It's another Greek alphabet, or another letter in the Greek alphabet. But again, the important thing is it's something we don't know. It's an unknown, but again, it doesn't make sense. It's, it's representing some angle between 270 degrees and 360 degrees. So could we do a rough sketch of that angle? And yeah, if I know here to here is 270 and all the way around is 360, then I can assume that phi is going to be some angle, some angle right around in there, right? So therefore, I can draw my triangle in the fourth quadrant. I know it's going to be a fourth quadrant. I'm not going to use phi. You could use phi. But again, representing that this represents the reference angle, you could use phi prime. Just really depend on, I'm not going to get into that because what we'll do is next class period, we'll kind of further understand the relationship between this angle and how to apply them. But for right now, we're just going to use another angle. In this case, I'll just use theta to represent that angle. But either way, we just really want to understand the quadrant and how we can arrive at the quadrant either by some trigonometric inequalities or just by using another inequality based on angles instead of trigonometric expressions. All right, so then let's go ahead and work again through another set. So in this example, we have secant of alpha is less than 0. So again, really what I like to do is just kind of identify what is secant. Again, secant is going to be r over x. So again, if that is less than 0, then I have the second quadrant, or it's going to be in the third quadrant, right? It has to be in one of those two. If tangent is less than 0, well, remember tangent is going to be a y over x. So therefore, that's either tangent is less than 0, that's going to be negative y over x, or that's going to be a positive, or that's going to be a positive y over a negative x. It's going to be one of the two. We don't know which one it's going to be, but it's going to be one of those two. So again, that's either going to be in the second quadrant, or that's going to be the case in the fourth quadrant. So you can see that in quadrant 2 is the only quadrant where that is going to be true for both of them. And therefore, I will just go ahead and draw the triangle there in that second quadrant, right? Because really the question was just what quadrant does the angle lie in? The next one here, we have sine is less than 0. So again, sine is going to be y over r. So again, if sine is less than 0, that's a horrible line, but that's kind of cool. Is less than 0, so that's going to be down here or down there. If cosine is greater than 0, then it's going to be over here or over here. So you can see that the only are true in this fourth quadrant. So let's go ahead and draw our triangle. And that one's going to be theta right there. So I'll just go ahead and use theta in that angle. There you go. Oh yeah, and cosine is just going to be, let's just write that in there, x over r. All right, the next one is now just giving some angles here. So we're going to have pi is less than beta, which is less than 3 pi halves. So again, now we're having an angle that's in radian form. So it's the same kind of idea. We know that halfway around the circle here is pi, right? So if we start here in standard form, here's pi, and then here's 3 pi halves. So it's going to be some angle right in there. And again, if I wanted to draw my triangle in this third quadrant, then I'm just going to draw it just like that. And I'll just go ahead and use alpha to fit in. But you can see basically that triangle is going to be represented in the third quadrant. And then last but not least here, we have 0 is less than y, which is less than 90 degrees, which is going to give me a triangle here in this first quadrant. Here's 0, there's 90 degrees, and there's your y. Okay, so again, fairly basic, but you're going to see here in the next set of examples why understanding the quadrant is going to be helpful for our problems. But we can just understand that this is going to be important because based on each of these problems are in different quadrants, and based on that information, we know that the trigonometric functions are going to be positive and negative, are going to be different for each one of these 4 problems because they're going to be positive and negative based on the quadrant that they lie in. And that's really the fundamental understanding that we need to take away from this lesson, is understanding how these constraints are going to impact our answers. So let's go and take a look at how our answers, or what type of questions we'll be go ahead and solving. So the first one was cotangent of x equals negative 2/3, and then we have a restriction cosine of x is going to be greater than 0. So we know that cotangent is negative 2/3, right? We write the negative in front. Again, remember that can mean negative 2/3, negative 2/3, or a 2/3. It just cannot equal negative 2/3, right? So what I told my students is like, we have 2 options, right? It could be this triangle or it could be that triangle, right? It could be, remember cotangent is x over y. So it could be negative 2, negative 2x, 3y, or positive x and a negative 3y, right? So it could be one of the 2. You don't know which one is which. Let's use x. I forgot to put in these angles. Then we got to look at the restriction. Well, the restriction says cosine of x is greater than 0. Well, what is the only one where, remember, cosine of x represents the x coordinate, right? So what is the only triangle where the x coordinate is positive? Well, obviously, you can see here the x coordinate is positive. So therefore, we're going to use that bottom angle. So I'm just actually going to put a big X there to remind you that is, when we're doing these 6 trigonometric functions, we are not referring to this triangle. And actually, what, let's just do. I'll just maybe do a line. There you go. So we're not referring to that triangle. Bad triangle. All right, let's go back. Oops, wrong one. Okay, so then I just evaluated the 6 trigonometric functions. Remember in the 4th quadrant here, the y coordinate's negative, so therefore I automatically can check my answers. I know sine and cosecant are going to be negative, as well as tangent and cotangent. And you can see sometimes I threw the negative in the numerator, or in the denominator in the numerator, and sometimes you can just put it in front, and it really doesn't matter. Typically, we always like to write it in front, but if you leave it in the numerator and denominator, that's perfectly fine. And what I ask my students to do is just kind of write the original function, and then they could rationalize the denominator, and if they needed to show their work, they could, but I am not going to be showing my work in this case for as far as rationalizing the denominator, because that's something we already covered, and I don't want to keep on spending so much time doing that because we do it a lot. However, I did want to bring up one other problem that we have, and that is with the sine of theta equals 1 over x, where cosine is less than 0. So this is a problem that we're actually going to be doing a lot of in this chapter. It's actually going to be something that we're going to tackle at the end of the unit, but I wanted to present it to the students for 2 reasons. One, so they understand that if I give them sine of an angle equals 1 over x, that is still a triangle. That's still opposite over hypotenuse, right? And we could still evaluate, we could still find the third side by using the Pythagorean theorem. Then the next part about this is that when you are evaluating, though the Pythagorean theorem, remember when you introduce the square root, the inverse operation of the square root is plus or minus, or the inverse operation of squaring is plus or minus the square root. So you have to include plus or minus again. We only stopped talking about that when a triangle was in space and negatives didn't make sense. But now negatives make sense. Like we know this orientation here, this is in the 2nd quadrant. Not all the sides are negative. So, and you can see A represents this distance to the left. So of course this distance has to be negative. Like if you write that distance, and I'll have this all the time when students take a quiz, is they'll draw the graph correctly, they have the side lengths correctly, but then they show this distance as being positive. And it's like, no, you're going to the left. This has to be negative. And that's why when you introduce, when we take the plus or minus here, that's why you can see we use the negative version. And again, I kind of finished the rest of the problem, so therefore those of you could kind of see how this works, but it's not really something that you're going to need to be concerned about, at least for the rest of this lesson, as far as how to evaluate those. But I really wanted to make sure students understood the plus or minus and how that comes up. All right, so now let's go ahead and work through some 4 different examples that you can kind of see are all different, are all the same. You can see that they, in each one of these, we have our trigonometric expression, kind of like what we did in day 1. But then we also have a constraint. And again, the constraint is going to tell us which quadrant we are going to be in. So I'm just going to kind of work through these individually, and we'll kind of see how their answers compare. So in this first example, we have sine of theta equals the square root of 3 divided by 2. So again, let's just remember, like the sine, represents the y over r, right? So I could plot this, but again, let's just kind of identify which quadrant we're dealing with. Cosine is going to be less than 0. So cosine is negative. So again, if cosine is negative, that means our triangle has to either be in the second quadrant or it has to be in the third quadrant. But it has to be in one of those two, right? If the x-coordinate is negative, less than 0, then it has to be in these two quadrants. So and then obviously, I can look at this. I'm not going to do like which quadrant it is and do where they intersect again, which you could do. But hopefully you can just recognize the sign is positive. So out of these two triangles, this triangle in the second quadrant, obviously the sign is positive. Here's where the sign would be negative. So drawing my triangle correctly here, I'm going to go here to here. So then this is going to be square root of 3, and this is going to be 2. Now again, I do not know my x value in this case, so therefore I'm going to use Pythagorean theorem. So I'm going to say 2 squared equals square root of 3 squared plus, I don't know, let's call this a again. A squared. So this is 4 equals 3 square root of 3 squared is just 3 plus a squared. And therefore, a squared is equal to 1. Subtract the 3, right? And then you're going to square root both sides. So therefore, a equals plus or minus 1, which again, we know that since we're going to the left here, we can see that a is going to equal negative 1. So again, that's very important because a lot of students will get 1 and they'll write a 1 there. But again, notice that we're going to the left. So that's why the my a is, in that case, negative. All right, so now we're just going to evaluate the 6 trig functions. So we have sine of theta is obviously already given to us. So that's awesome. The cosine of theta is going to be negative 1 over 2. And the tangent of theta is going to be square root of 3 over negative 1. And again, if you look at this summary here, if you look at that summary, and I'm just going to simplify these from there. But if you look at the summary here, that again, it makes sense. Like cosine and tangent should be negative in this second quadrant. Now let's go ahead and do the reciprocals, whereas sine is positive. So the cosecant of theta is going to be the reciprocal. So that's going to be 1 over the square root of 3 over 2. You could do it that way, or we talked about, it's just the flipped version, right? It's just 2 over the square root of 3. So now I could rationalize the denominator, and I get 2 radical 3 over 3. The secant is just the reciprocal of negative 1/2, which is just giving me a negative 2. And the cotangent of theta is going to be the reciprocal of negative square root of 3. So that's going to be 1 over negative square root of 3. Again, you could rationalize the denominator, put the negative in the top or the bottom. Just don't put it in both, or put it in front. In this case, you get square root of 3 over 3. All right. So that's basically we're going to be case. We're going to, utilize which quadrant we could be in. And sometimes you might just want to put in your options. Like for instance, I have tangent of alpha is negative. So if I think about that summary, I have 2 options here. Tangent of alpha is going to be negative either in the second quadrant, like we just explained, or in the fourth quadrant. Whereas sine is less than 0, that is only going to be true in the third quadrant and the fourth quadrant. So just kind of by using visualizing this, and again, you could go through drawing the triangle like I did in this first example and doing your options, or you could do the first problem that I did and actually, draw 2 hypothetical, identify the quadrants and see where they, intersect. But in this case, you can see that the only triangle that makes sense is in the fourth quadrant. Now I do recommend though, that you still draw this triangle to make sense of it, right? So if this is going to be in the fourth quadrant, then let's make sure we understand where it's going to be. Now, again, we don't know where the negative goes, is it in the top or the bottom, but since it's in, since we're doing it in the fourth quadrant, we recognize that, this is y over x, right? So we know that the x is positive and the y is going to be negative. So this would be a negative square root of 3, and this would be a positive 3. Here's your angle alpha. So again, by looking at this triangle, does this make sense for the tangent? Yes, negative square root of 3 over 3 would be negative, and the sine, the y-coordinate, is negative. So it's, this is going to work. No other quadrant that you could play around with is going to satisfy that. So now we have our triangle. Now we just evaluate the 6 trig functions. Just make sure now we're taking into consideration that is a negative square root of 3. So the sine of alpha, we can't do the 6 trig functions until we know what our hypotenuse is. So, also at this point we start doing the Pythagorean theorem in our head. But let's just kind of work it out here, and let's just call this r squared. So 3 squared is 9. Negative square root of 3 is just going to be, again, a positive 3 equals r squared. And then in this case, we're going to have 12 equals r squared. So in this case, we don't have a nice little number, right? We're going to have r is going to equal the positive square root of 12, right? So you square root both sides. Now, it's very important that, remember, r is always positive, right? So we don't need to worry about the plus or minus because r in this case is always positive. However, we do have to simplify our r. So by simplifying the r, remember that the square root of 12 can be broken down into 2 radical 3. All right, so now we have our r, which is 2 radical 3. And now let's do our 6 trigonometric functions. So sine of alpha is going to be opposite over hypotenuse. So it's going to be negative square root of 3 over 2 radical 3. Well, the square root of 3's are going to divide out, so that's just going to leave us with a negative 1/2. The cosine of alpha is going to be adjacent over hypotenuse, so that's going to be 3 over 2 radical 3. Rationalize the denominator here. So that's going to be 3 radical 3 over 6, which can be reduced to square root of 3 over 2. Let's see here. The tangent of alpha, we already have that answer, right? So that one's easy. Then let's work on the reciprocal functions. Now, again, we want to do as least amount of work as possible, right? So rather than flipping, our original ratio, let's just flip our final answer, which would just give us a negative 2. Rather than flipping this ratio, let's flip our ratio over here. So this is secant of alpha. It's just going to be 2 radical 3 over 3. And then tangent here, cotangent. I'm actually going to go back to the triangle. Cotangent of alpha, because I don't really want to reciprocate that, but the cotangent, remember, is x over y, which again, you're not going to really get away from it then. So it's a negative 3 over the square root of 3. Rationalize the denominator is a negative 3 square root of 3 over 3, which equals a negative square root of 3. Just trying to fit that in all the way at the end. So you can see here, really kind of the same numbers, it just involved a little bit more simplifying. But again, and also there's their difference because this was in quadrant 2 and this is in quadrant 4. So the trigonometric functions are different, right? And I know that the sine and cosecant as well as the tangent, cotangent are going to be negative. All right, so now let's get into some fun ones. So here we have secant of theta equals negative 4. Now again, remember secant is r over x. Well, we don't have an r over x, we just have a number. But remember, trigonometric functions are a ratio. They are a comparison. How big is the hypotenuse compared to the adjacent side? So that means we need to write this as a fraction. So to do that, we can just write this as negative 4 over 1. But remember, secant, secant of theta is equal to r over x. So when we have negative 4 over 1 is incorrect because r is never negative, right? So it's not going to be the fact that, this triangle doesn't exist. But again, we can rewrite this as 4 over negative 1, which makes a lot more sense. R is positive and my x is negative. So if my x is negative, I know I'm dealing with here the second or the third quadrant. My tangent is positive, right? So again, remember tangent is y over x. So if it's positive, that's going to be in the first quadrant. Obviously, everything's positive in the first quadrant. Or in the third quadrant, because negative y over negative x also gives me a positive. So therefore, you can see that the only quadrant that they both are true in is going to be the third quadrant. So I'm going to draw a triangle in the third quadrant. So that's going to be 4. That's going to be negative 1. I'm going to use Pythagorean theorem here. So we have 4 squared equals negative 1 squared plus, I don't know, b squared. That becomes 16 equals 1 plus b squared. So let's see. So b squared equals 15. And then square root. You can see b is going to equal b is going to equal the square root of 15. Sorry. That's going to be plus or minus the square root of 15. And again, we notice that we're dealing with something that's in the third quadrant. So therefore, this is going to be a negative square root of 15. Again, very important to understand that distinction, that why it has to be negative. So now let's go ahead and evaluate my 6 trigonometric functions. So we have sine of, what are we doing? Theta. Okay, so sine of theta in this case is going to be opposite over hypotenuse, so that's going to be a negative. I'll just put the negative in front, negative 15 over 4. The cosine of theta is going to be a negative 1/4. And the tangent of theta is going to be opposite over adjacent. So again, remember tangent is positive, right? A negative over negative is positive. So that's going to be a negative square root of 15 over negative 1, which is just a positive square root of 15. So now let's go to the reciprocal functions. So cosecant of theta is going to be hypotenuse over opposite. So that's a reciprocal. So it's going to be 4 over the square root of 15. Rationalize the denominator here. You're going to have a negative 4 square root of 15 over 15. For the secant of theta, that's just going to be a negative 4. And then for the cotangent of theta, that's going to be a positive 1 over the square root of 15, which equals the square root of 15 over 15. Bang. All right. Last example. Last example here, I have cosine of alpha is positive, right? And it's 5 over 13. If it's positive, then I'm dealing with the first or the fourth quadrant. And then I recognize the cosecant of alpha is also positive. Well, again, I can just actually stop here. If I know both things are positive, it has to be in the first quadrant, right? Cosecant obviously is only going to be positive in the first and the second. But again, the main thing that if you have something that's positive, then it's going to always be in the first quadrant. Or I'm sorry, when both terms are quadrant, it's going to be in the first quadrant. The other nice thing to notice about this is that you could use the Pythagorean theorem, right? X over R, or you could recognize that this is a Pythagorean triple. So, I would write out the, x squared, or I'm sorry, let's do this as 5 squared plus, a squared equals, c squared, or I'm sorry, 13 squared. But hopefully you recognize here that we have done these problems, or we've introduced you before, that's actually going to be 12. And again, if you do the math, 13 squared is 169, minus 25 is going to be 144. The square root of 144 is 12. Since it's in the first quadrant, it's going to be positive. And the nice thing about this is now our trigonometric relationships are pretty easy, right? So we have the sine of alpha is going to be, 12 over 13. The cosine of alpha is going to be 5 over 13. The tangent of alpha is going to be 12 over 5. And now our reciprocals, we don't need to worry about our radicals at all. So therefore, our cosecant of alpha is 13 over 12. Our secant of alpha is 13 over 5. And our cotangent of alpha is 5 over 12. So there you go, ladies and gentlemen. That is basically how our 6 trigonometric functions are going to change, or at least our problems are going to change if we are given a constraint. Because in the first lesson, we didn't have constraints. So we were just doing the exact same process for a triangle in space. But now you can see that orientation matters, right? It gives us now these negatives for side lengths that make sense based on the quadrant that the triangle lies in. However, we've been so focused on, finding the trigonometric functions given a triangle or given an expression. What if we were just given a point? So again, we can always create a triangle, right? If we have a coordinate point, this is x, y, and this brings up into why we started just plotting points. You can always just plot the point, square root of 3, comma 1, plot that point. We know square root of 3, again, is going to be some decimal between 1 and 2. So, I just kind of drew a graph there and I said, all right, that's going to be square root of 3 and that's going to be the height is 1. So those are the side lengths of my triangle. I draw my right triangle correctly. And then I did the Pythagorean theorem here to figure out 2. So we're finding the hypotenuse, which is r. So therefore, we know that it's going to be a positive 2. And now, based on this point, I know it's in the first quadrant. So that's nice. Everything is going to be positive. And from this point, I can create a triangle. So therefore, I can evaluate the 6 trigonometric functions. Now, you really don't need the 6 trigonometric functions or the triangle because remember, the only 3 points that you need is x, y, and r, right? From our new definition today, all we needed was x, y, and r. Now again, remember r, x squared plus y squared, and this is really kind of important. I didn't actually tell my students about this. X squared plus y squared equals r squared, right? Because r represents that hypotenuse. So without actually drawing a triangle, if you know the quadrant that the point is in, and you can figure out x, y, and r, based on our new trigonometric definitions, you could actually evaluate all 6 trig functions. Now, what typically happens? Most students just are comfortable evaluating the 6 trig functions from a triangle, and that's why I am going to teach it with drawing the triangle every single time. It's not that much extra time, and it also is just a good way for you to verify your work and check your answer. But the more comfortable you get with these problems, you can for sure just figure out x, y, and r and go about your way. Now, again, in this case, let's just say it was a multiple choice problem. Even just with the xy here, we could solve for xy, right? You could just say, you could solve the xy. You could solve for tangent and cotangent though, because for tangent, cotangent, you don't need to know r. So you could just solve those without actually doing anything rather easily. All right, but let's go and look at some 4 different examples to kind of see how they differ and how this is going to help us with our understanding of these types of problems. All right, so here we have a couple points here, and you can see that they don't really look that pretty, right? Maybe B and D are not too right, but these do not look like that fun. So let's go ahead and give them a shot. Now, as far as graphing, 2 square root of 2, comma 2, I'm not even gonna, we could figure that out. We could, estimate, but in this case, let's just forget about it. Like, we just know it's gonna be positive, right? And we know that's gonna be larger than 2. So what I'm gonna do is I'm just gonna put this point over here. I'm not even gonna put any scales, because I don't want to overcomplicate the problem. We know that this side is 2 square root of 2 and this side is 2, right? I mean, that's it. You don't really need to know anything more except that it's in the first quadrant and that those are the side lengths of the x and the y, the adjacents, right? That's your x and that's your y. That's your adjacent as well as your opposite side. We could go ahead and use the Pythagorean theorem though to figure out our hypotenuse, which we know again is going to be positive. Let's call it r squared. So again, 2 square root of 2 is going to be 4 times 2, which is going to be 8. Plus 4 here is r squared, so that's going to be 12 equals r squared. So again, we have r equals, we already did this one, so that's going to be a 2 radical 3. Is that what I wanted from this? Huh. 2 radical 2, let me just double check. That's going to be 4. I guess I wanted this one. Doesn't look as fun, but all right. I just want to make sure I had that one correct. That's 8. That's 4. Now my brain is hurting. So 2 square root of 2, that's going to be 4 times 2, which is 8, 12. Okay, yeah, it works. So let's go ahead and evaluate. So the sine, now again, what angle should we do here? We can do anything, right? So I'm just going to use theta to make things easy. So sine of theta is going to be, this is 2 radical 3. So therefore, sine of theta is going to be 2 over 2 radical 3. I can rationalize the denominator here. The 2's are going to divide out, and that's going to give me square root of 3 over 3. For the cosine of theta, that's going to be adjacent over hypotenuse. So that's going to be 2 radical 2 over 2 radical 3. And therefore, again, you're going to have radical 6 over the 2's divide out again. So in this case, you're going to have a you're going to have a radical 6 over 3. And then we have tangent of theta. Again, I'm just doing the rationalizing in my head because that's something I've already covered. Tangent is going to be opposite over adjacent, so that's going to be 2 over 2 radical 2. The 2's divide out, so then you're going to have radical 2 over 2. All right, so now let's go ahead and get into the reciprocal functions. So we have cosecant of theta, which is going to be just this reciprocal here. So just flip that over. That's going to be the square root of 3. Here we're going to have secant of theta, which is just going to be, let's see here, that's going to be, really the 2's divide out. So we can just, I'll just leave it up there. Square root of 3 over 2, square root of 2. Rationalize the denominator here. That's going to be a square root of 6 over 2. And then we have the cotangent of theta is going to equal 2 square root of 2 over 2, which is just the square root of 2. And there you go. So again, knowing that simplifying, so I wrote the original ratio and then I just simplified it. And I didn't show my simplifying work because that's something we already covered. The next one here, I have a coordinate points here in the fourth quadrant. Again, you could draw it out if you want to, but we know it's in the fourth quadrant, right? The x and the y are both negative. So therefore, that's a -6 and that's a -8. All right. Well, hopefully you guys also recognize that this is a Pythagorean triple. So you could do the Pythagorean theorem if you need to. But hopefully you guys recognize that that hypotenuse is going to be 10. Because 8 squared is 64, plus 6 squared, 36. 64 plus 36 is 100. Square root of 100 is 10. And of course, it has to be positive because r is always positive. So the sign, let's call this one different. Let's do this one as alpha. So the sign of alpha is going to be a -8 over 10. And again, we want to reduce these fractions, right? We can simplify these fractions. So dividing the top and bottom by 2, that's going to be a -4/5. The cosine of alpha is going to be adjacent over hypotenuse. So that's going to be -6 over 10, which can be reduced to a -3/5. And then the tangent of alpha is going to be the opposite over adjacent. So that's going to be a -8 over -6, which again can be reduced to a +4/3. Okay, so again, just making sure that you simplify and then also make sure that in the fourth quadrant that you can check sine and cosine should be negative and tangent should be positive. So now when doing the reciprocal functions, I'm not going to do the original. I'm just going to do the simplified version here. All right, I'm just going to do a -5. Oops, forgot the equals. So -5/4. For the secant, it's going to be a -5/3. And for the cotangent of x, or cotangent of theta, alpha, it's going to be a +3/4. So you can see once you've already kind of done the work once, you can really evaluate. All right, my favorite two problems. Two problems that students struggle with, which of course, who wants to go ahead and do this? Nobody, right? But there's something that's really important about this problem that kind of comes up that I used as an instructional piece when I was instructing. And then also this -1, 0, which is something we're going to talk more about in our next lesson. But let's go ahead and find the quadrants and then at least kind of go through these two problems to understand what they mean. So hopefully you recognize that this point is going to be, that's the x and that's the y. So it's going to be some triangle in the third quadrant, right? So we have -3/2, +3/2. Okay, so let's do Pythagorean theorem just like we do any other problem and see what we're going to get. So we have -3/2 squared plus a +3/2 squared equals r squared. So here we're going to have 9/4 plus 9/4 equals r squared. So that's going to give you 18/4 equals r squared. Now you could introduce the square root, right? So r is going to equal the square root of 18/4 plus or minus. Don't forget that. But again, we actually don't really need to include the plus or minus, right? Because we know we're just dealing r, so it's just going to be the positive version. And therefore r is going to be, now we can just simplify that as the square root of 18 over the square root of 4. Legal process, okay? And the square root of 18, remember that can be broken down into 3 square root of 2. So r equals 3 square root of 2 over 2. Now again, you can't divide out the 2's, right? One's on a radical, one's not. But I think it's really important for me to write this out. 3/2 times the square root of 2. All right, so here's the important thing. Here's what I want students to see. Nobody wants to do the 6 trig functions with the triangle like this. Nobody wants to do the 6 trig functions with a triangle like that. That is going to be way too many simplifying, way too much work to do. One thing I noticed is that the 2 legs are the same and that the hypotenuse is multiplied by the square root of 2. The legs are the same and the hypotenuse is the exact same of the leg, just multiplied by the square root of 2. And hopefully what that does is that brings up, oh, that is a 45, 45, 90 triangle. And again, remember, the trig functions, guys, are the exact same. It doesn't matter what the size is of the triangle, right? If they are proportional, they're going to have the same. They're going to have the same trigonometric functions, right? Because trigonometric functions are ratios. So what I could do here is you could use that triangle if you wanted to. Or what if you multiply all the sides by 2, right? That's a dilation in geometry. It's going to enlarge it, but it's going to have a scale factor. So it's going to keep the proportions intact, or the ratios, the trigonometric ratios intact. But if you multiply by 2, right, times by 2, you now have 3, -3, and 3 square root of 2, which is a little bit better, right? I like that. But what about now, let's make it even easier. What if now you divided by 3? Well, if you divided by 3, now you would have 1, -1, square root of 2. That is a lot easier for me to be able to evaluate my 6 trig functions. And you might even be as well versed in the 6 trig functions to already know what the trigonometric functions are, because we've already talked about our 30, 60, 90 triangles. But we'll use that as triangle if that's something that you are not familiar with. And I'm going to write this as beta. So sine of beta. Now again, it's in the second quadrant, so I know sine is positive. I'm just going to go ahead and go through my answers. Actually, you know what? I already know the answers for a 45, 45, 90 triangle. So I'm just going to write that in there. It's a 45, 45, 90 triangle. So I don't expect students to know the answers, at least in this point, but I know those answers, so I'm going to work with it. The cosine of beta, though, is cosine's negative, right, in the second quadrant. So that's going to be negative square root of 2 over 2. And the tangent is going to be negative. And tangent doesn't matter if it's these two fractions, these two, or these two. We know it's just going to be a -1. The cosecant of beta is now just going to be negative square root of 2. So when you flip that and rationalize the denominator, not negative. What am I doing? The secant of beta is going to be that's going to be the negative square root of 2. And then the cotangent of beta is going to equal, again, also a -1. So again, you could have worked out the relationships here, but basically we've already kind of talked about this 45, 45, 90 triangle and those values. So therefore, I'm just working it with that. All right, on to the last point. Again, is a very, very important understanding here, because if you take the point -1, 0, we have an issue because that does not create a triangle. So how are we going to evaluate the 6 trig functions without a triangle? Like, is that even possible? Should we just write not possible? You could, but let's go and investigate this a little bit further. Because I was trying to be really careful when I was describing these values that we're finding, the x, y, and the r. Yes, we can create a triangle, draw a perpendicular line, create a triangle, and go from there. But in reality, remember, x represents this horizontal distance, y represents this vertical distance, and r represents this direct distance, right? So if we take this point and, we kind of rotate it like around here, right? We know that x in this case is -1, y is going to be 0, and then r, again, if you just think of r as what is the distance from the origin to that point, you can say that r is going to be a +1, right? R is always positive. So r represents a +1. Now, again, all we need for our 6 trig functions is x, y, and r. And we have exactly what we need. So we actually can evaluate the 6 trig functions when we are not given a point that creates a triangle. We can actually use this information to evaluate our 6 trig functions. So let's do sine of, let's just go back to theta. So sine of theta is, again, just going to be y over r. So that's going to be 0 over 1, which is just equal to 0. The cosine of theta is going to be x over r. So that's going to be -1 over 1, which is -1. the tangent of theta is going to be y over x. So that's going to be 0. Wait a minute, what did I do? Sine is, 0 over r. Okay, tangent is y over x, so that's 0 over -1, which is just equal to 0. So now the reciprocals, though, we have something that comes into play here, because cosecant of theta is 1 over 0. And if you remember, we can't divide by 0, right? So this actually is undefined. The secant of theta is just going to be 1 over -1, which is also -1. So secant, cosine are actually the exact same. Interesting. And therefore, cotangent of theta is now going to be -1 over 0, which is, again, also undefined. So we'll talk more about that from now. But I just want to make sure that you understand, really, when we're given a point, drawing the triangle is important, or at least knowing the quadrant that the triangle in is also important. But then also realizing that really we just need to figure out these x and y's, and remember that proportionality, right, matters. Like if you need to simplify the problem, as long as you're multiplying or dividing all the sides of the triangle by the same number, you are keeping those triangles proportional with each other, and therefore the trig functions are going to remain the same. So always kind of think about that. You know, I don't want students to be spending 20 minutes trying to do the 6 trig functions and then getting the exact same answers that I got here in a fraction of the time. But hopefully that this lesson kind of helps you out, at least understand those constraints a little bit more, because we're not just going to be dealing with triangles in space. We are going to be dealing with triangles where the orientation matters. So hopefully you can reflect on what made sense for you on this lesson and what things you're still struggling with. And I look forward to reading your answers and helping you out on the next video. Cheers.